High in Peru's Andes, giant stones lock together with a precision that seems impossible. No mortar, no gaps, just blocks the size of buses, fused as if they were cut by machines.
You cannot fit a dollar bill or a razor blade between them. The technique of fitting these blocks together baffles archaeologists and engineers today.
For centuries, experts measured, debated, and guessed, but nothing explained how it was done. Now, new scientific breakthroughs are finally peeling back the mystery, and what they reveal is stranger, darker, and far more real than anything you've heard before. Stick around. This will blow your mind. Inside Peru's megalithic ruins. When you get up into the highlands of Peru, the first thing that hits you isn't just the thin air. It's the walls. These aren't regular walls either. They look like something straight out of a magic trick. The kind of construction that makes you stop and ask, how the hell did they do this back then? Let's start with Sacsayhuaman, sitting more than 12,000 feet above Cusco. From far off, it looks like the side of the hill has been carved into 3 giant zigzag walls, like a giant knife carved deep grooves into the mountain. But when you walk up close, that's when it really hits you. The blocks that make up those walls are so massive that they make you feel tiny. Some are the size of buses. The biggest weigh anywhere from 140 tons to well over 200 tons, and yet they're stacked so perfectly that you can't even slide a sheet of paper between the seams. No mortar, no glue, just raw stone pressed so tight it looks like one solid surface. And the wild part? Those stones didn't even come from right there. They were hauled from a quarry called Rumicolca, sitting more than 20 miles away across rough Andean mountainsides. You can still hike out to that quarry today and see half-finished blocks, the scars where workers cut out massive chunks before abandoning them. Now move about 40 miles northwest into the Sacred Valley, and you run into Ollantaytambo. Here, the land pinches into a tight valley with steep walls on both sides, and climbing above the little town is Temple Hill. Right at the top sits one of the most jaw-dropping pieces of Inca stonework, the Wall of the 6 Monoliths. These aren't small building blocks either. Each one is a huge pink volcanic slab, cut and hauled from quarries called Cachicata across the Urubamba River. That's about 3 miles as the condor flies, but don't let that number fool you. Hauling something that size down cliffs, across a river, and back uphill into position is insane. And the proof is still sitting out there today. The quarries are scarred with abandoned blocks and half-finished cuts, almost like the builders dropped their tools one day and just never came back. Ollantaytambo itself sits around 9,160 feet, so think about the logistics of dragging stones that size across that kind of terrain. It's no joke. If you stand up on Temple Hill and look across the valley, you can see Cachicata clear as day. The whole mountainside is carved up, scarred with cuts, slides, and leftover blocks. An architect named Jean-Pierre Protzen studied the area and confirmed that the same reddish stone used in Ollantaytambo's monolith wall came right out of that quarry. Whether you call it rhyolite, ignimbrite, or even granite, like some older notes do, you can spot it instantly by the color and texture. It doesn't match the regular cobbles in the valley. The choice was deliberate. They didn't just use whatever was lying around, they went after a specific stone. Then there's Machu Picchu, probably the most famous of them all. Perched on a razor-thin ridge at about 7,970 feet, the site is sandwiched between 2 peaks, with the Urubamba River looping far below. From the postcard view, it looks like terraces and stone buildings glued to the mountaintop. But the real secret is under the surface. What you don't see is the thick foundation of packed fill, gravel, and stone that ties the whole place into the ridge. That hidden substructure is the reason Machu Picchu hasn't collapsed down into the valley after centuries of rain and earthquakes. And remember, the river sits almost 1,500 feet below those plazas, so if that foundation wasn't there, the entire site would have been washed away a long time ago. When you line all these sites up, Sacsayhuaman, Ollantaytambo, Machu Picchu, you start noticing the same patterns: stones shaped to interlock, corners softened and rounded, joints cut so they taper slightly inward. And the choice of stone wasn't random either. The Incas loved volcanic rocks like andesite and diorite. These are seriously tough materials, filled with hard minerals like plagioclase and quartz. On the geologist's hardness scale, those minerals sit around 6 to 7 out of 10. That means they're hard enough to hold a sharp edge, but not impossible to shape with patience. Back in Cusco, Sacsayhuaman sprawls across a high ridge above the old city. It's not just those 3 zigzag walls. The place once had towers and wide plazas on top, like a fortress combined with a ceremonial center. At more than 12,100 feet, the altitude itself is a challenge. Just walking around leaves you winded. What's striking, though, is how the walls are laid. The stones are polygonal, many with multiple sides, and they lock together like puzzle pieces, and each course doesn't stand perfectly vertical. They lean slightly inward, bracing themselves against the slope. You don't need to be an engineer to see the logic. Wide base, tight seams, walls angled into the hill. Ollantaytambo, on the other hand, tells a different kind of story. The little town below still follows the same grid the Incas laid out, with canals running through its narrow streets. Machu Picchu mixes the same ideas, but in its own style. The ridge is divided in half. One side is lined with over 100 agricultural terraces that grip the slope like stair steps. The other side holds temples and houses with the classic Inca look: trapezoid doors and windows, inward-leaning walls, and joints so tight they don't need mortar. And those aren't the only sites. Take Pisac, perched on a ridge north of Cusco. Its terraces wrap around the mountain in graceful curves, tied together with clusters of houses, towers, and stairways. Or Tipon, sitting southeast of Cusco at elevations between 10,700 and 13,000 feet. It looks like a water garden carved into the mountain. Straight canals run across green terraces, and ceremonial fountains spill sheets of water from basin to basin. The American Society of Civil Engineers even recognized Tipon as a historic engineering marvel. And then there's Moray. Instead of terraces hugging slopes, Moray drops them down into the earth. 3 massive circular depressions cut into the ground, each ring a terrace bench. From above, they look like perfect amphitheaters. From inside, they're 100 feet deep bowls, ring after ring of stone. Zoom out, and all of this sits in one of the harshest building environments you can imagine. The Andes aren't calm mountains. Off the coast, the Nazca Plate dives under South America along the Peru-Chile Trench. That collision created the mountains and still triggers earthquakes today. The Incas were building entire cities on narrow ridges and steep slopes in a region that constantly shook and shifted. That's why their choices weren't just about looks, they were about survival. Slopes, rivers, and quakes forced them to adapt. What we can see tells us a lot about size and layout, but it doesn't answer the question on everyone's mind: how on earth were these stones cut, hauled, and set in place? The Incas' genius method for building the impossible. So here's the big question: how did the Incas move and shape stones so massive without steel tools, cranes, or modern machines? To figure that out, you have to start at the quarries, because that's where every single block began its journey. For the huge projects in Cusco, most of the stone came from Rumicolca, a giant quarry of andesite rock sitting more than 22 miles from the city. Archaeologist Dennis Ogburn even traced stone from Rumicolca not just into Cusco, but unbelievably far north, hundreds of miles away. Why drag blocks that far? Because it was a message. It was imperial branding carved in rock. If the empire could haul a block across mountains and drop it in a plaza, that wasn't just construction, that was intimidation. Everyone who saw it knew who was in charge. At Ollantaytambo, the setup was a little different. The quarry was closer, right across the Urubamba River, at a place called Cachicata. Hike there today, and you'll still see abandoned blocks scattered along the route. The locals even call them tired stones. They tell you the story. Workers rough-shaped the block at the quarry, slid it downhill onto ramps, dragged it to the river crossing, hauled it over at a shallow ford, then pushed it back uphill on switchbacks to Temple Hill. A Nova team once tested that very path with a real block and a real hauling crew, and it worked. The ramps worked, the crossing worked, and the uphill grind, while brutal, was possible. No cranes, no forklifts, just human muscle and smart planning. And the proof is in the stones. Geologists matched the pink volcanic rock of the famous Wall of the Six Monoliths at Ollantaytambo directly to Cachicata. It's rhyolite or ignimbrite, and it doesn't match the valley cobbles. But here's the big question. How do you even split a block that size without steel chisels or diamond saws? The answer is almost boring: patience. The Incas looked for natural cracks in the rock. They chipped grooves into those cracks using hard river cobbles as hammerstones. Blow after blow, wedge after wedge, they weakened the stone until it split. Jean-Pierre Protzen, an architect who spent years experimenting in an actual Inca quarry, proved it. He used the same method, and the tool marks he left behind matched perfectly with what you see on Inca blocks. It's not magic. It's thousands of careful, repetitive hits. That's why you see rounded inside corners in Inca stone joints. Sharp 90-degree cuts are nearly impossible with hammerstones, and honestly, not even needed. Protzen's tests showed that the surfaces left behind looked exactly like Inca walls. Rough centers with smoothed edges where the blocks touched. Nova's experiment confirmed it using the method called scribing. Here's how it works. Press two blocks together, mark the high spots, pull them apart, peck down the bumps, and repeat. Do that over and over until the stones lock together so tight a blade can't slip between them. No saws, no secret chemicals, just trial, error, and grinding patience. If you look carefully at many blocks, you'll see little nubs or shallow notches sticking out. Those weren't mistakes, and they weren't decorative. They were practical. Builders used them as grip points, places to tie ropes, jam levers, or control rotation. They're like built-in handles. And when a block face wasn't going to be public, sometimes they didn't even bother removing them. You can still spot these on walls in Cusco and Ollantaytambo, frozen evidence of how the stones were handled. So how do you move a stone that weighs 100 or 200 tons across steep Andean slopes? The trick is, you don't try to do it all at once. You move it in short, controlled bursts. Stones were dragged on sledges or on their own faces, but always along prepared paths. Workers built cobbled ramps or compacted earth tracks, so the blocks slid instead of digging into the ground. The Nova test proved this too. On cobbled ramps, the hauling crew could actually control the block. On raw dirt, it just stuck and dug trenches. Crossing the river was no mystery either. You wait for the dry season, pick the shallowest ford, throw in a forest of ropes, and hundreds of hands later, the block is on the other side. No wheels, no oxen, no pulleys, just planning, surfaces, ropes, and teamwork. And here's where the Empire's real advantage came in. It wasn't just the stones, it was the roads. The Incas built one of the largest road systems in the ancient world. Today, we call it the Capac-an. More than 18,000 miles of routes stretched across deserts, rainforests, and mountain passes. There were staircases, paved sections, and causeways linking quarries to towns and temples. This road network is so impressive that UNESCO lists it as a World Heritage Site all by itself. That's how they kept the machine running. Roads carried the crews, the tools, the food, and yes, the stones. But roads don't move blocks by themselves. You need people, and that's where Mita came in. In Quechua, Mita means a work turn. Instead of paying tax in money, communities paid it in labor. People rotated in and out, spending weeks or months on state projects. In return, the empire fed them from huge storehouses stocked with maize, potatoes, and dried meat. Smithsonian researchers describe this clearly. It wasn't slavery, it was organized community labor, and it scaled perfectly. With thousands of workers rotating through, there were always enough hands to haul ropes and drag blocks forward. Animals helped, but only for smaller loads. Llamas were the backbone of everyday transport, but each one could only carry 70 to 100 pounds. That's perfect for food or tools, but useless for blocks weighing dozens of tons. Ethnographic accounts and museum exhibits agree. Llamas kept the empire supplied. But when it came to stone, it was human strength that did the heavy lifting. Finally, once a block arrived at the construction site, it wasn't simply dropped into place. Builders worked through a cycle. They set it roughly on a prepared base, checked the fit, pulled it back out, chipped down the high points, then set it again. Over and over, until it locked in perfectly. Pratzen showed that hammer stones alone can carve the little beveled edges you see on clean Inca joints. Nova's tests showed how efficient the scribing method was. You only remove the spots that touch, not the whole face. Multiply that by hundreds of blocks, and you get a wall where every stone hugs its neighbors like custom-made Lego. The geometry of the blocks helped too. Multi-sided stones keyed into each other, and the walls leaned inward as they rose. That tilt wasn't for looks, it was structural. It made the walls lock tighter under their own weight. Step back, and suddenly, it all makes sense. The process wasn't supernatural or impossible. It was smart, and it left fingerprints everywhere. You can still walk quarries littered with half-finished blocks. You can still find ramps, cobbled ways, and abandoned, tired stones stuck mid-route. You can see nubs left on blocks for rope handling. You can run your hand over seams polished only where two stones touched. All of it adds up to one thing: a system that was slow, grueling, but absolutely effective. We've cracked the method of building, but the real shocker is why those walls are still standing when everything else around them has crumbled. Why Inca walls never fall. What really stuns people about the Incas isn't only how they built these massive walls, it's how those same walls are still standing after centuries of punishment from earthquakes, storms, and unstable ground. Think about it. These cities sit on thin mountain ridges that shake constantly, get hit with months of rain, and deal with erosion all year. Colonial buildings and modern walls have collapsed again and again under the same conditions. But the Inca stonework, it stays put. That's not some miracle, that's careful design. Cusco is the clearest example. Back in the year 1650, a massive earthquake ripped through the city. Colonial houses and churches crumbled, but the old Inca walls, built of giant stones fitted without mortar, stood tall. 300 years later, in 1950, another strong quake shook Cusco. The pattern repeated. The newer lime and mortar walls split open and fell, while the Inca stonework barely budged. Engineers even studied the damage patterns to figure out which direction the ground had shaken. The stones themselves told the story, and the lesson was obvious. Inca walls were designed to flex, shift, and settle back in place, while later walls were brittle and failed. A lot of this comes down to the shape of the walls. Look at them closely. They don't rise straight up. They lean slightly inward as they go higher. Builders call this a battered wall. That inward lean acts like a wedge, pushing the weight back into the hill behind it. Then look at the blocks. They're not simple rectangles. They're multi-sided stones, cut like puzzle pieces. Engineers call this polygonal masonry, and it works because the seams don't run in straight lines. They zigzag and cut off any long crack that could split the wall in one motion. Shake tests and computer models confirm it. Walls made of puzzle-shaped blocks and leaning slightly inward can take far more shaking than neat rectangular walls stacked like bricks. If you zoom in on the joints, you'll notice small steps and rounded corners where stones meet. Those details aren't decoration. They act like brakes. When the ground jerks, one stone starts to move, then hits a step or curve on its neighbor and slows down. Because the walls are dry stone, with no mortar, nothing brittle cracks under pressure. Gravity and friction hold everything in place. During a heavy earthquake, individual blocks can even rock slightly, then settle back into position once the shaking stops. Modern experiments and digital simulations have confirmed this exact behavior. The design is brilliant because it allows movement without collapse. Even the openings follow the same logic. Inca doorways and windows are wider at the bottom and narrower at the top. That shape spreads the load sideways like a tripod. And instead of sharp right angles that act as weak points, the Incas rounded the corners. Stress that would normally crack a sharp edge just flows around it. Once you see these choices, it becomes clear. Every single angle, every cut, was made to stop cracks from running and to make sure the walls could bend without breaking. Now let's talk about Machu Picchu, because this is where the hidden engineering really shows. Everyone knows the postcard view of terraces climbing the ridge and temples hugging the summit. But what you don't see is that most of the work is underground. Civil engineers who studied the site estimate that about 60% of the construction is hidden. Massive foundations, stone drains, and thick layers of engineered fill. Without those invisible supports, Machu Picchu would have collapsed long ago. This ridge gets between 75 and 80 inches of rain each year. Without drainage, the soil would turn into mud and slide off the mountain. But the Incas built Machu Picchu like a giant filter. Beneath every terrace and plaza are layers of gravel, sand, and stone. Rainwater seeps down through the soil into the gravel, then flows sideways into drains. Pressure never builds up. Slopes stay stable, and plazas don't flood. That's why the site has lasted so long. The water supply was engineered with the same care. A natural spring fed the city, but its flow changed with the seasons. Measurements show it could drop to just 7 gallons per minute in the dry months, then rise to 33 gallons per minute in the wet season. To handle that, the Incas built a canal capable of carrying up to 79 gallons per minute, far more than the maximum spring flow. That gave the system plenty of headroom, so it never overflowed. The canal carried water past storage buildings and then fed 16 fountains in a row, each one steady and clean. And here's the part that shows just how smart the design was. The drinking water line stayed completely separate from storm drains. Even during heavy rain, runoff couldn't contaminate the supply. That's the kind of detail you'd expect in modern civil engineering. But the Incas had it centuries ago. The terraces, too, weren't just for farming. They were multi-layered engineering systems. At the base of each one sat coarse rock. Above that, smaller stones. Then, a layer of gravel. Finally, a thin cap of topsoil. Rain fell on the crops, soaked through the soil, filtered into the gravel, and drained out. That stopped water from building pressure behind the walls and kept the slopes from failing. Excavations of broken terraces show this exact structure, and engineers who studied them say it's the reason the terraces have lasted hundreds of years without reinforcement. Tipon is another perfect case study. It's a mountainside site southeast of Cusco, where water runs through a series of stone channels and fountains. Streams drop from basin to basin in smooth, steady sheets. The joints are tight. The drops are even. and the water never splashes wildly out of control. Hydrologists who studied Tipon called it a masterclass in flow engineering. The channels resist silt buildup, the layout prevents clogging, and the design is clearly planned for long-term use. You don't get that kind of control by chance. It takes exact measurements and precise construction. Moray tells the same story in a different way. It's a circular pit, nearly 100 feet deep, carved with concentric terraces. Scientists measured temperatures inside and found differences of up to 27 degrees Fahrenheit between the top and bottom on the same day. That created microclimates. Seeds planted at different levels were exposed to different conditions. The stone walls trapped heat, the curved terraces cut the wind, and the bowl shape held air like a pocket. Moray was basically an agricultural laboratory, tuning crops to different environments by design. Modern technology has only confirmed what the stones already show. Engineers used 3D laser scanning to build precise models of Machu Picchu, Tipon, and other sites. They checked slopes, wall angles, terrace grades, and drain positions down to the inch. At Cochabamba, another Inca site, they used both ground and drone scans to model a water channel and test its flow. Ground-penetrating radar revealed buried features without digging. In every case, the numbers lined up with the visible design. The walls leaned as intended, the terraces drained as planned, and the canals carried the right capacity. Nothing was accidental. And the Incas didn't just think about walls. They applied the same resilience everywhere. Stairs were built wide and low, not steep and narrow. Stairways hugged walls so they couldn't separate. Terraces broke long slopes into short steps, stabilizing the ground. Storm water was guided along channels instead of cutting random gullies. Drains were routed far from foundations, so bases never washed out. Even fountains are discharged onto stone pads to stop erosion from splashing. None of these choices looks dramatic on their own, but together they created systems that could take enormous stress without breaking down. And that's why, centuries later, the world still stares at these places in disbelief. Not because the methods are mysterious, but because they worked so well. These weren't just monuments built to impress. They were entire systems built to endure. And in one of the toughest environments on Earth, they're still doing their job. Thanks for watching. See you in our next video.